Hello everyone. Today we will be talking about Gauss Markov theorem. So what does Gauss Markov theorem state? Gauss Markov theorem states that the ordinary least square estimates for the regression that we have studied, OLS, these OLS are actually best linear unbiased estimator. Okay. So that is, if we want to consider the class of unbiased estimators, then the ordinary least square estimates are best among them. In what sense an estimator is best? When we say best, it means that they have minimum variance. Okay, minimum variance and unbiased. So basically, we are trying to prove that OLS are minimum variance unbiased estimator. Okay, this is the statement of Gauss Markov theorem. Now, here is a small problem. See, even in the simple linear setup, my estimate beta, my parameter beta is a vector, and as a result, my estimate is also a vector. Okay, and of course, in multiple linear regression, it is p-dimensional vector. Okay, I will have beta naught, beta 1 up to beta k, where k plus 1 is p. So I have to talk about variance of a vector. And we know variance of a vector is nothing but a matrix. So how can I say a matrix is minimum? I cannot really minimize the matrix. So what we do is, in such a situation, we prove that variance of any linear combination, if we consider with respect to, so variance of L prime beta hat, if I consider, then that variance should be less than or equal to variance of L prime into any other estimator, let's say beta star. Okay, so if I consider, and this should happen for every L in RP. Okay, so if I consider linear combination of my OLS estimate, any linear combination, then variance of that linear combination should be smaller than variance of the similar linear combination computed with other estimate in place of beta hat. Okay, this is what we have to prove. Now, what is variance of L beta hat? Let me first write that L prime beta hat. So variance of L prime beta hat, we know from the multivariate theory, it is L prime variance of beta hat into L. So this is L prime. Variance of beta hat we know is sigma square x prime x inverse, correct? And L. Sigma square is common. It's a scalar, so it can be taken out. So this is sigma square L prime, then x prime x whole inverse L. Okay. This is our variance of L prime beta hat. What we have to prove is, if beta star is any other estimate, then we have to prove that variance of beta L prime beta star, which is equal to L prime variance covariance matrix of beta star into L, this should be larger than or equal to sigma square L prime x prime x inverse L. Okay, this is our requirement. We have to prove this. How do we prove this? See, we are talking about best linear unbiased estimate. Okay, so linearity is also important. So this is not minimum variance unbiased estimate in any class. It is minimum variance unbiased estimator in the class of linear estimates. Okay, that's why we are saying it is blue. Okay, best linear unbiased estimate. So the beta star that we are considering also has to be a linear estimate. Okay, what do I mean by that? It means that I could write beta star as some matrix. Okay, we could write beta star as some matrix, let's say M into Y, then only it will be a linear estimate. Okay, if I can do that, maximum what we can have is addition of some constant to this. So it could be some my plus some b naught. Okay, so what does it mean? If it is a linear combination, then I could find a relationship between this beta star and our beta hat. So I could write this as m and then my. I could have plus our usual beta hat. Usual beta hat is x prime x whole inverse x prime y. We will subtract that because we want to make we want to keep the equation intact. X prime x whole inverse x prime y. Okay, and then plus beta naught is as it is because it is some constant. Okay, so this I would write as my plus this is beta hat. Okay, this is beta hat minus I will keep as it is x prime x whole inverse x prime y plus beta naught. So now what I'll do, I will write this as m minus x prime x whole inverse x prime whole thing into y plus beta hat plus b naught. Okay, so I could write this matrix as some B matrix. Okay, so I could write m minus x prime x whole inverse x prime. I'll give a new name to it. So that is b y plus beta hat. Okay, this is a vector, not a matrix. I'm sorry. Plus b naught. Okay, so what I've done, we have just added and subtracted. So on LHS, we have the new estimate that is beta star. So I could write this as beta plus, because I know beta hat is x prime x whole inverse x prime y. We will keep like this y plus b naught. Okay. So what we have done is this is b, this is not beta, this is b. So this is b plus this beta hat we are writing as x prime x whole inverse x prime into y. Okay. So we have expressed the new beta star as something like this. Now, first let us consider expectation, because we have to worry about only the class of unbiased estimates. Okay. So expectation of beta star will be this matrix. B matrix is anyway a matrix of constant. So B matrix into expectation of y. Okay. So let me write this as B plus x prime x whole inverse x prime expectation of y plus b naught, because b naught is anyway a constant. So this will become b times expectation of y, okay, plus x prime x whole inverse x prime expectation of y. Expectation of y we know is x beta under our model definition plus b naught. Okay, our model definition says y equal to x beta plus epsilon, and hence expectation of y is x beta. Okay, so this gets cancelled, x prime x inverse and x prime x. So I am left with b expected y plus b naught plus of course this beta. Okay, beta coming from the second term. So let me substitute what is expectation of y. So that is b times x beta, correct? Because expected y is x beta plus b naught is as it is plus this beta is as it is. So this expectation, we want expectation of beta star to be beta because we want an unbiased estimate. So this expectation will be beta, that is expectation of beta star will be equal to beta if and only if bx is equal to 0 and b naught is equal to 0. Okay, because if bx is non-zero, then I would have an additional term here, so beta star won't be unbiased. Okay, so we have to assume that bx is 0 because then only then only beta star will be an unbiased estimate. Okay, now with these conditions in mind, let us compute variance of this new estimate beta star. Okay, so it will be variance of, we have written a form for this beta star. Beta star is this. What is beta star? It is this. Where is it? Okay, so we will consider this form. Beta star is by plus beta hat plus b naught. Now b naught is anyway 0, so just by plus beta hat. So this will be variance of by plus beta hat. Okay, let me write the formula for beta hat. So this becomes variance of by plus x prime x whole inverse x prime y. Okay, so this becomes variance of b plus x prime x whole inverse x prime, and this whole thing into y. The other thing is constant, so we know that this becomes of the type variance of something, some matrix times y. So I will have the matrix, that is b plus x prime x inverse x prime into variance of y into prime of that matrix, that is b plus, b is a matrix, okay, b plus x prime x inverse x prime. Okay, of course prime of this a sigma a prime kind of thing. Variance of y we know is sigma square I, so I won't be in picture, so I'll simply have sigma square sitting over here. Okay, so I have b plus x prime x inverse x prime into prime of this matrix. Prime of this matrix will be b prime plus prime of the inside thing is x into x prime x inverse, because x prime x is a symmetric matrix, x prime x inverse is also a symmetric matrix. So this is sigma square into, let me take the product, so I'll have b prime plus b x into x prime x whole inverse plus x prime x whole inverse into x prime into b prime plus x prime x whole inverse into x prime x into x prime x whole inverse. Okay, and just now we proved here that for beta star to be unbiased, bx has to be 0. Okay, bx has to be 0 means what? Means this term has to be 0, and of course transpose of it is also 0, so x prime b prime is also 0. So I'm left with only the first term and the last term. Okay, so this becomes sigma square b prime plus x prime x whole inverse x prime x gets cancelled, so I will have x prime x inverse. Okay, this is x prime x inverse. Okay, this is my variance of beta star. Now let me consider variance of any linear combination of beta star. So I will have variance of L prime beta star. So that will become L prime into this variance, that is B prime plus x prime x inverse into L. So this becomes L prime B prime L plus L prime. Of course, sigma square is sitting over here, so I should have sigma square here, and then sigma square into L prime x whole inverse L. This we know is variance of beta hat, our OLS estimate. Okay. So if we could prove that this quantity, sigma square is anyway non-negative. So if we could prove that this quantity is greater than or equal to 0, then we are done. Okay. So L prime, so I have to worry about L prime, B prime, L. Okay. Let me just write it. I have to worry about L prime, B prime, L. What are the orders? Order of B is same as x prime x. X prime x has order P cross P. Correct? L prime is P cross 1. Sorry, L prime is 1 cross P. So this is 1 cross P, P cross P. This is P cross P and P cross 1. So if I consider just this part, L prime B, then it is a vector. Okay. So let me consider, let us assume that D is equal to B prime L. D is a new vector of order P cross 1 such that D is B prime L. Then this quantity is simply D prime D, okay, which is equal to summation Di square, correct? I going from 1 to P. Because it is square, because it is norm of a vector, it has to be greater than or equal to 0, okay? And in fact, as soon as one of the LIs is non-zero, it has to be actually strictly positive. Hence, we have now proved that variance of L prime beta star is greater than or equal to variance of L prime beta hat. Okay? Yeah, here I missed it. This is variance of L prime beta hat, not variance of beta hat. Okay? L prime beta hat. Thus, what we have proved is variance of L prime beta star is greater than or equal to variance of L prime beta hat. Okay? Hence, we have established that in the class of linear estimators, linear unbiased estimators, beta hat has the least variance. This is the statement of Gauss Markov theorem. That is, the ordinary least square estimates are blue, that is best linear unbiased estimator. Okay, let me stop here. Thank you.